So now that you know a little bit about extended free body diagrams and what torque is, we're ready to start doing some problems for objects experiencing balanced torques. So I've got set up here something really similar to the simulation you used. I have a 200 gram mass and then a 100 gram mass. You'll notice the 200 gram mass is half the distance from this center point as the 100 gram mass is. So this one has twice the distance, half the mass, twice the mass, half the distance. Now, I also have the pivot point set up right here in the middle. A really important point here is when this pivot point is right at the center of mass, this force of gravity alone on the meter stick is not enough to cause it to rotate. So it does not exert any torque, no matter how big that force of gravity is, because it's pushing straight down on that pivot point. Now what I want to think about is, what if we move that pivot point? So I've moved my clamp to the far end of my meter stick. So now all of a sudden, with this physical setup, the pivot point is down here. And if I hang my mass from the meter stick, it's now exerting a torque, trying to rotate the meter stick that way. And I can still balance this if I exert some upwards torque on the end. Or rather, this is going to be a counterclockwise torque. So this is something I'm going to do as an actual problem. So for reference, I have this clamp at 4 centimeters. I have a 200 gram mass at 50 centimeters. And I've got my spring scale at 78 centimeters. So using the setup that I just showed you and the numbers I pulled from that, I want to figure out what is the mass of the meter stick I was using. So the first thing I'm going to do is make an extended free body diagram. Just like the first thing we do with a balanced forces problem is make a regular free body diagram. Now, as part of that, I need to decide what I'm going to use as my pivot point. And a really useful one for this is going to be, if I make right where that stand is, my pivot point. Now, while that is what the meter stick physically tends to rotate around, just because that stand is fairly fixed, it also is a pretty useful one to use, because we can put that pivot point wherever we want to. We can choose any point along this meter stick we want. In this case, the big advantage of making that stand the pivot point is I don't have a way right now to know what force does that stand exert. But if I make that stand's location the pivot point, it's not going to exert any torque. And so I can do a torque problem that ignores this force. But I am going to have to pay attention to these other forces. So I'll go ahead and I'm going to label the force that this mass exerts on my meter stick. I'm going to call that normal force 1, because that hanger is exerting a normal force on the meter stick. Now, this R1, the distance from what I chose as my pivot point to where this mass is, this mass is at the 50 centimeter mark. Now that's 50 centimeters from the very end of the meter stick. So that means the distance from the pivot point is actually 46 centimeters. Now, I also have a force that this scale is exerting. That scale exerts 2.4 newtons. I'm going to call that a spring force. And it's exerting that force upwards. Now it's at a position of 78 centimeters. So when I read off the meter stick, it was 78, which means its distance from the pivot point is going to actually be 74 centimeters. If I do 78 minus the 4 centimeters from the end. Now there's one more force I don't have on here yet, and that's the force of gravity on the meter stick itself. And that's going to act on the meter stick's center of mass, which is right at 50 centimeters. So right in the same place where I had that hanging mass. Now, the next thing I'm going to do is think about which way each of these forces would cause the meter stick to rotate. So if nothing else was here, if the meter stick was just pinned down right at that pivot point I picked, and the only force acting on the meter stick was that hanging mass, that meter stick would tend to rotate this way, which is clockwise. So I'm going to think of that as a clockwise torque. That force of gravity is also a clockwise torque. Now my scale, on the other hand, because of where it's located relative to the pivot point, is exerting a torque the other way, counterclockwise. So there's not necessarily a hard and fast rule for whether torque or whether a given force exerts a clockwise or a counterclockwise torque in terms of whether it's above or below or pointing up or down. I always just think through, if this were the only force acting on this thing, which way would it rotate? And then I do these little arrows to help myself keep track, because that's going to tell us whether we have to add the torques or subtract them. So the normal force from the mass and the force of gravity, they're exerting torques in the same direction. So I'm going to say the torque from that hanging mass plus the torque from the force of gravity equals the torque from the spring scale. Now you'll notice I'm using the same subscripts that I did on the forces up above. And that's just to help remind me that these torques are a result of those forces. So now the next thing I'm going to do is use that torque is force times distance. So instead of the torque from normal force 1, I'm going to say the value of normal force 1 times its distance from the pivot point plus the force of gravity on the meter stick times its distance from the pivot point, which happens to be the same as the distance that normal force 1 is. Those two together have to equal the force from the spring scale times the spring scale's distance from the pivot point. So now I'm ready to do some rearranging to get that force of gravity by itself. If I'm solving for the mass, if I can find what the force of gravity has to be, then I can take another step and get what that mass is. So the first thing I'm going to do is subtract from both sides to get to something that looks like this. So the force from the spring scale times its distance minus the normal force from that hanging mass times its distance. Now the next thing I'm going to do, I'm going to replace the force of gravity on the meter stick with the mass of the meter stick times lowercase g, and that's just off our formula sheet. And I haven't done anything to this right side on this step. But now what I can do is I can divide both sides by g times r1 to get mass by itself on the left. So then I just have to do the spring force times the spring scale's distance minus the normal force of that hanging mass times its distance, all divided by little g times r1. So when I plug in numbers, so that spring scale, I just read off the scale that it exerts a force of 2.4 newtons, and it is 74 centimeters, which is 0.74 meters from the pivot point. Now the normal force that hanging mass exerts is going to be the same as the force of gravity on that hanging mass, which is 0.2 newtons. And it is 0.46 meters from the pivot point. Then, if I do little g is always 10, I'm going to use newtons per kilogram here. And then that R1 is 46 centimeters, which is 0.46 meters. Now, if I take a real quick look at my units, I have newtons in both terms on top, and I have newtons on the bottom, so that's going to cancel. And then same thing with meters. That leaves me with just units of 1/kilograms on the bottom, which means my answer will have units of kilograms, which absolutely makes sense for a mass. So if I plug this in, I get 0.37 kilograms as the mass of my meter stick, which I dropped the meter stick on a kitchen scale I have just to double check, and I happened to get 0.37 kilograms, which is a good sign. So now what I want to do is look at another question we can answer with this setup, and that's going to in particular lead us to changing that pivot point. So the next question is, I want to know what force does that stand exert on the meter stick. Now, that pivot point we used before is not going to work for this question, because to figure out what force the stand exerts, I need it to apply some torque. But I mentioned that the pivot point is arbitrary. So what I'm going to do, I'm going to choose right there for my pivot point. Now, I could have put that pivot point anywhere along the meter stick that I wanted. The reason I picked right here is that that gets rid of two forces. Neither that hanging mass or the force of gravity is going to exert a torque on the meter stick around this pivot point. So if I could somehow pin that meter stick in space right there, the hanging mass and the force of gravity would not be able to cause it to rotate. So from there, this is going to be a fairly similar problem. So my scale is 0.28 meters from this new pivot point, but the size of the force it exerts is still the same, and it's going to exert a counterclockwise torque. Now if I go over here, I'm going to call this normal force 2. And I don't have a number to put with that, but I do know that it is 46 centimeters away from this pivot point, which is 0.46 meters. Now if I were to imagine this force rotating the meter stick with it pinned at that center point, this would exert a clockwise torque. So this is an example of where forces that are both pulling upwards can exert opposite torques. So now that I've got my extended free body diagram, because I know that these are exerting opposite torques, that means that the torque each of them applies must be equal to each other. Because those are the only two torques, and because they're acting in opposite directions, they have to be equal to, or have the same value. So I'm going to start with that. And then, really similar to what I did before, I'm going to replace torque with force times radius. And then I'll do the same thing for the scale. And you can see that with just two torques, this is a fairly straightforward equation. The algebra is not going to get too hairy on this one, which is nice. And so a lot of times with a clever pivot point, you can make the algebra relatively nice. So, to get this normal force by itself, I'm just going to divide both sides by that distance, which gets me here. So, when I put in numbers, I'm going to have the force the scale exerts, which is 2.4 newtons, times the distance the scale is from the pivot point that I'm using now, which now that distance is 0.28 meters. And then the distance the stand is from that pivot point is 0.46 meters. If I check my units, I've got meters on the bottom and meters on top, so those cancel out, which leave me with units of newtons, which is what I expect for a force. And when I plug this into my calculator, I get 1.46 newtons. Now, there's one last step I'm going to take, and that's to use what I know about balanced forces to just double check my math here to make sure that this 1.46 newtons is correct. So what I know is that because my meter stick was at rest, the net force must also be balanced. So that means that my upward forces, the force from the scale, plus the normal force from the stand, those must equal the total of all my downward forces, which are the force of gravity on the meter stick plus the normal force from that hanging mass, which I called normal force 1. So if I wanted to use this to find the force the stand must have exerted, I can move the force from the scale over to the right side to get something that looks like this. And then I'm going to go ahead and plug in numbers. So the force of gravity on the meter stick is 0.37 kilograms times 10 newtons per kilogram, so that's going to be 3.7 newtons. We already used that the normal force from that hanging mass is 0.2 newtons. And we were able to read off the spring scale that the force is 2.4 newtons. And when I plug all of that into my calculator, I got 1.5 newtons, which is pretty darn close to that 1.46 newtons I calculated using torque,
which suggests that I did indeed do this correctly.